first laudatio will be the laudatio for Artur Avila, and it will be given by Etienne Ghys. Etienne, please.
Artur Avila is a fantastic dynamicist. If I had to give a summary of 4 centuries of research in dynamics in 2 minutes, I would say that there are 4 main stages in this history. The first was initiated by Newton. You are given an ordinary differential equation, and your task is to find its solutions. It was a remarkable success, the success of differential calculus. The second stage began when Poincaré, at the turn of the 20th century, understood that in many cases, it is simply impossible to find a formula for the solutions. This is, for instance, the beginning of chaos theory. You are given an ordinary differential equation, and your task is to say something about its solutions. If possible, something interesting, like, for example, describing the qualitative behavior of the solutions when time goes to infinity. And the third stage began when mathematicians understood that in practice, physicists never know the equation they want to solve. There are always unknown quantities that may be small, but which may have some influence on the motion. This period began, say, in the 60s with Smale and Thom. You are not given a differential equation, and your task is to say something about its solutions. This is the main area of research of Artur Avila. Most of his papers turn around the question, what does a typical dynamical system look like? But before I go into some details, let me introduce you quickly to this young man. Artur was born in 1979 in the beautiful city of Rio de Janeiro. He got his PhD at the age of 21 under the supervision of Wellington de Mello at IMPA, the Institute for Pure and Applied Mathematics in Rio. We should know that a Fields Medal never blooms in the middle of nowhere. The approach of Smale and Thom of dynamics has been one of the main forces of IMPA in the last 50 years. IMPA can be proud of this medal. Later, but still very young, Artur went to Paris, where he got a CNRS position. Maybe he could catch there some of the spirit of Poincaré. Today, he holds a double academic position in Rio and Paris, and a double nationality, Brazilian and French. This is a wonderful, successful international collaboration. Artur is very open-minded. He likes to share ideas with others. He has a huge number of collaborators. And the best I can do for you today is to show you this diaporama of his collaborators. This is a good illustration of the modern way of doing mathematics, taking full advantage of the internet and of Skype. Artur is a problem solver. he wrote many papers solving many conjectures. I'm sure you can understand that it is a daunting task for me, even an impossible task, to give you an overview of his mathematical contribution. Even more so, since my intention is not to speak to the experts, and my dream would be to be understood by all of you. I have to be impressionistic and to make some choices among many other possibilities. Artur is an analyst. Let me go to some example. Start with what we call a unimodal map. It's just a map from the interval to itself with a single maximum. That's it. I'll assume for simplicity that the second derivative at the maximum is negative. Pick a point x, take its image, f of x, and iterate the process. You get a sequence of points, fn of x. And your task is to say something about this sequence fnx. Where does it go? Where does it accumulate when n goes to infinity? But do not forget the message of Smale and Tom. Don't try to do it for every f. Try to do it for a typical f. Here is one of the very first important statements of Artur right after his PhD, together with Michal Lubitsch and Wellington de Mello, and improved a little bit later with Gugu. You have a non-trivial real analytic family F sub lambda of unimodal maps as before, and the theorem is that there is a dichotomy that for almost every lambda, the map F lambda is either regular or stochastic. Of course, I should tell you what means regular and what means stochastics. A regular map is the easy case. It means that if you pick a point at random x, the orbit fnx converges to a periodic orbit. This is the easy case, non-chaotic, very simple to understand. Typically, the set of values of lambda for which this happens is open and dense in the parameter space lambda. And the second case, stochastic, is the complicated case. It is the chaotic case. However, the word chaotic should never be understood as a negative word. It does not mean that you cannot predict the dynamics of the map F. There is a measure which is absolutely continuous with respect to Lebesgue, and which is such that almost every orbit in 0, 1 is distributed according to this measure, unless it goes to periodic motion. So in this case, we are very happy because the dynamics is completely understood through this beautiful measure mu. The set of values of the parameter lambda for which this happens has positive Lebesgue measure. And the theorem I mentioned earlier is that the union of these two cases, the regular case and the stochastic case, the union of these two cases has full Lebesgue measure. This theorem has a long history. Unfortunately, I have no time to explain the details, but I want to say that this is one of the first instances in which a special case of a conjecture of Pallis has been checked, describing the typical behavior of a typical trajectory of a typical diffeomorphism. According to Michal Lubitsch, you could say that we have reached a full probabilistic understanding of real analytic unimodal dynamics, and Artur Avila has been the key player in the final stage of the theory. Of course, it's impossible for me now to give you even a hint of the proof of such difficult theorems. The only thing I can do is to say something about the main tool in the proof. Artur is certainly not the inventor of the renormalization operator. However, very quickly, he began to be the best user of it. Most of his papers use the renormalization operator. It became his magic stick. It was the subject of his plenary talk in the previous Congress. So let me explain what it is. Suppose you have some dynamical system, like a map F, from a set X to itself. And suppose that in X you have a subset X1, a small part X1, which is such that every point in X1 has an orbit which comes back to X1, maybe after many iterates. So this defines a map F1 from X1 to itself, sending each point to its first return in X1. In many cases, the small x1 is somehow similar to the big X. So usually there is some kind of zoom out from X1 to X. So you can look at the map X1, not from X1 to X1, but from X to X. And you get a map R of F from X to X. This operator R is sending a dynamical system on X to some other dynamical system of X. This is the renormalization operator. And the miracle is that the dynamics of R as acting on the space of dynamical systems is very much related to the dynamics of a typical F acting on F, on X. So as Adrien Douady used to say, we first plow in the dynamical plane and then harvest in the parameter plane. Let us have a look at the first historical example. Here's a unimodal map from the interval to itself, F. Let me square it. F composed with F. You get such a map. And you see that F squared preserves some subinterval. So you can zoom F squared from this subinterval to the full interval, like that, and then flip it, and you get another unimodal map. So what I just described for you is a dynamical system acting on the space of unimodal maps. Here's a general picture. In the late 70s, Coulet-Tresser and Feigenbaum had the intuition, based on numerical evidence, that the renormalization operator R acting on the space of unimodal maps should have a fixed point. This fixed point is called a Feigenbaum map, and the dynamics in the neighborhood of this fixed point should be like that. There should be a one-dimensional expanding direction and a co-dimensional one attracting direction. It was a long and fascinating joint venture of many mathematicians to transform this intuition into a theorem. Many mathematicians, including in particular Lanford, Sullivan, Macmillan, Lubitsch and Avila could achieve Sullivan's dream to transform a proof which was basically a computer-assisted proof in a brain-assisted proof. After some kind of technical preparation, the proof boils down to the simple use of the Schwarz lemma. a proof from the book, as Erdős would have said. Let me switch gears and let me go to some other kind of dynamical system, billiards. Imagine you have a box containing a gas of bouncing particles. Imagine, even though this is not physically realistic, that the gas is so dilute that the particles do not collide between themselves and only bounce on the boundary. So each particle basically is following a billiard ball game. They bounce on the boundary. What is the corresponding dynamical system? Let us assume for simplicity that the box is two-dimensional and is actually a polygon. If you choose a point x on the boundary and a direction v, say of length 1, if you hit a ball from x in that direction, the ball will bounce at the point x prime and bounce in a new direction v prime. And of course, the dynamical system you want to understand is the map T sending xv to x prime v prime. Let us make an additional assumption. Let us assume that the angles of the polygon are rational multiples of pi. In such a situation, the velocity after bouncing on the boundaries takes only a finite number of values. Like, for example, if you play billiard in a rectangular table, the velocity takes only 4 possible directions. So this reduces the dynamics from dimension 2 to dimension 1. For each segment on the boundary of your polygon, you have a finite number of possible directions, so you have really a dynamical system acting on the union of a finite number of intervals. This kind of dynamics is called an interval exchange. Technically speaking, it's very easy. You start with an interval, you split it into sub-intervals, you permute the intervals, and you reorganize that. So the black goes to the black, the blue to the blue, the red to the blue, etc., etc. Do not ask me questions concerning the endpoints. Forget them. So the dynamics of a rational polygonal billiard in the plane is basically reduced to understanding the dynamics of an interval exchange map. Now let me state the theorem of Avila and Forni, 2007. Almost all interval exchange transformations are weakly mixing. So I should explain the words. Almost all should be easy, because the space of interval exchange maps is finite dimensional. If you want to describe an interval exchange, you have to choose some permutation, and you have to choose the length of the intervals. So this is a finite dimensional union of finitely many simplices. So you have the Lebesgue measure at your disposal, and these almost all interval exchange maps, this almost all is relative to the Lebesgue measure. Mixing, weakly mixing. Before I explain the word weakly mixing, let me explain mixing. Suppose you have a map, x, f from x to x, which is preserving some probability measure mu. One says that f is mixing if the limit when n goes to infinity of the measure of A intersection f and b is the product of the two measures mu A, mu b. Somehow, this means that as time evolves, the dynamics forgets the past. The events f and A and b have a tendency to become independent in the probabilistic sense. So this is a good approximation of randomness. Weakly mixing, as you can guess, is just a weakening of mixing. It's just the following. You have the same definition, except that you allow the integer n to go to infinity staying in a subset of the integers of full density. I put definition of density here. This is not important. A significant set of integers is a set of full density. So really, weakly mixing and mixing are essentially the same concept. Now coming back to the theorem, almost every interval exchange map with respect to the Lebesgue measure is weakly mixing. This is a major progress in the understanding of the dynamics of billiards. What about the proof? What is the main tool of the proof? Guess it. Renormalization. The renormalization map acts on the space of dynamical systems, which in this case is a finite dimensional space, and the miracle is that the renormalization map R turns out to be chaotic. Even though interval exchange maps are not chaotic, this chaoticity of the renormalization map acting on the space of interval exchange maps, this chaoticity is the key to understanding the dynamics of a typical typical interval exchange map. This is a tour de force. Let me again switch gears and go to some other subject where the dynamical insight of Artur radically changed the landscape. Quasi-periodic Schrödinger operator. Imagine you have some kind of a one-dimensional discrete quantum particle. So the phase space of this quantum particle is the Hilbert space of square integrable functions psi from Z to C. And you can think of the probability for a particle to be at point n to be proportional to psi n squared, modulus of psi n squared. As usual in quantum dynamics, the motion of the particle is governed by the Schrödinger equation, I times time derivative of psi is given by h psi, where h is the operator, which is written here. H psi n is psi n plus 1 plus psi n minus 1 plus v n psi n. The first two terms are just a discrete version of the Laplace operator. Vn is some bounded function, bounded potential, which describes the environment of the particle. And what you want to understand is the dynamics of this particle moving on the line. Note that H is a self-adjoint bounded operator acting on a Hilbert space. And as we all know, everything depends on the spectrum of this operator and the spectral measures. Let me remind you that the spectrum sigma is the set of energies E such that the operator H minus E times identity is not invertible. And the spectral measure associated to a state psi is the probability, is a measure mu psi, such that the integral of a function g with respect to this measure is given by this formula, inner product of psi with gh psi. This is standard, of course, in functional analysis. This spectrum and this spectral measure are relevant for the understanding of the dynamics of the quantum particle. Look, basically one could say the following. If the measure mu is absolutely continuous with respect to Lebesgue, this means that you are in a conductor regime. The particle travels freely on the line. If the measure is singular continuous, the particle travels but not as well. And if the measure is pure point, this means that the particle is trapped by the potential. So understanding the nature of the spectral measures and the spectrum is exactly the same thing as understanding the dynamics of the particle. The easiest example to look at is when the potential V is quasi-periodic. If you wish, you can think of a quasi-crystal. And among the easiest example, the easiest example is so-called almost Mathieu operator, when there is only one frequency. Vn is 2 lambda cosine 2 pi n alpha, is the standard example you want to understand. It was conjectured that when alpha is irrational, the spectrum is a Cantor set. In 1981, Mark Katz offered 10 martinis for the proof of this conjecture. And Barry Simon coined the term the 10 martini conjecture. Here's the so-called Hofstadter butterfly. If you slice this picture by a vertical line whose first coordinate is alpha, you see the spectrum of the operator for the value lambda is equal to 1, the so-called critical value lambda is equal to 1. So it gives you this beautiful fractal set. Indeed, Artur and collaborators came with new ideas, changing completely the field. Artur basically had the idea of incorporating ideas from dynamical systems in this spectral theory business. It is fair to say that spectral theorists had exhausted their toolbox and they didn't know what to do next. Artur came with ideas from dynamical system and could solve most of the conjectures which were open in this area. Let me mention 3 of them. Theorem by Avila and Zhytomyrskaya, the 10 martini conjecture. When alpha is irrational, the spectrum is indeed a Cantor set. Unfortunately, they didn't get the 10 martinis because unfortunately Mark Katz had passed away in 2009. 2006, Avila, Krikorian, Aubry, Andrea's conjecture, the Lebesgue measure of the spectrum is given by this formula. Actually, the case where, the non-critical case when lambda is not equal to 1 was already known by Zhytomyrskaya and Krasovsky. And the last theorem I wanted to mention is Avila, Zhytomyrskaya, and Avila, Damanik. For all irrational alpha and lambda less than 1, the spectrum is purely absolutely continuous. So if lambda is less than 1, you are indeed in the conductor regime. The quantum particle travels along the line. To finish, I wanted to mention a theorem which, strictly speaking, is not very much related to dynamics. It's purely partial differential equation theorem. I like it very much because it's easy to state and hard to prove. So Artur told me that almost every mathematician listening for the first time to the statement of this theorem is immediately convinced that this is trivial and offers a trivial proof, which is always wrong. This is a hard theorem. Maybe somebody in the audience will find a 2-line proof, I don't know. So let me give you the statement. Let me begin by something very easy and well known. Take a compact manifold, which is, say, infinity. Take a C1 diffeomorphism. It is well known and easy to prove that you can approximate it in the C1 topology by a, say, infinity diffeomorphism. Easy. Now the theorem is the same, except that you had a volume. So you start with a compact manifold of class, say, infinity, equipped with a C-infinity volume form. You take a C1 volume-preserving diffeomorphism, and the theorem of Artur is that you can approximate in the C1 topology this C1 diffeomorphism by a C-infinity diffeomorphism which is volume-preserving. The proof is wonderful. It goes by induction on the skeleton of triangulation. It reminds me of the wonderful proofs of Gromov of the H principles. Artur is a phenomenon in the modern theory of dynamical systems. His results are amazing, and I'm really convinced that this is just a beginning. Congratulations, Artur.